Thank you for the nice introduction. Maybe he's the only guy who pronounced my name exactly. I pronounce my name again. I'm Seung-Hoon Han, and from just the affiliated institute of ETRI. Wow. So many people are here for my talk, and thank you for attending, and especially thank you for the board members here. This talk is a little bit theoretical, so I will spend much time to explain my page-oriented programming and show the demo. Before starting my talk, I would like to introduce myself. I'm a senior script researcher at the affiliated institute of ETRI, and I'm a review board member of Black Hat ACI and KimchiCon conference. I was a speaker at several conferences like Unix Security, Black Hat USA, ACI Europe, Hack in the Box Script Conference, and more. Additionally, I'm a Debian Linux maintainer and have contributed several Linux kernel patches too. Goal of this presentation: first, I present weaknesses of the state-of-the-art kernel CFIs. Hardware and software-based CFIs only focus on indirect branches, but all CFIs, including kernel CFIs, need non-writable code. But it is only ensured by the page-level protection mechanism. Second, I introduce a novel and page-level code reuse attack called page-oriented programming, POP. POP utilizes the weaknesses of the kernel CFI. It programs page tables within the kernel to create new control flows with an existing kernel memory read and write vulnerability. You know, the word existing means that this talk doesn't explain how to find vulnerabilities. Yep, I know who you are, and you already had many kinds of vulnerabilities in your hands, so please use them for my POP, not for me, please. If you are not that kind of person, please ask around you and be careful. This talk comes from a huge mistake that I made. Many of you, hovering is so big. Yeah, many of you already knew and made the mistake. One person meets another person and imagine the bright future together and like a journey. Can you guess what it was? Maybe you know that. No? Yeah. I know what you imagine now. And in my case, it was a PhD journey. You know, I met my professor and imagined my graduation together, and yes, just forget it. And anyway, I can't understand why people call it a journey, but it is called like that. And the problem started because of it. You know, before starting my PhD, my brain whispered to me like, bro, I got many ideas and many algorithms, you know, and we can make it, bro. I swear, yeah, it really did. And after that, my brain was changing in real time like this. As you see, my brain has, novel algorithms and novel ideas changed to no ideas and no algorithms. I felt like someone stole my brain and put something happy instead of it. And I know. I shouldn't have to trust in my brain. It's also me, right? When I was dying because of the betrayal of my brain, one day, one of my colleagues saved me with these words. What a secure word. Control flow integrity is everywhere. As you see, these words have some sensitive points like secure and control flow integrity. Those means that control flow integrity, as known as CFI, can make a secure word. I think the secure word hasn't come yet because I know what you are doing at work and free time. So how can I imagine the secure world? Even I stand here because I could break the CFI, right? So it was enough to wake up my brain, and yeah, I'm here to present my research result now. So this presentation is about breaking hardware-assisted kernel control flow integrity with page-oriented programming. It's also the title of my talk. So first, I will explain control flow integrity briefly and hardware-assisted kernel CFI. After that, I will introduce a novel and page-level code reuse attack, page-oriented programming, POP, and show how to break the CFI with it. This is content, and now CFI. Control flow integrity is based on a control flow graph as known as CFG. The CFG contains all legitimate execution flows of a program. It can be generated from static and dynamic analysis and has two kinds of edges, forward and backward. Forward edges consist of indirect calls and jumps. Backward edges consist of returns. The CFI monitors the execution flows with the CFG and at runtime and prevents control flow deviations like control flow hijackings. This page shows the original CFI. Sort2 function has two function calls. The first call goes like this, and the second call goes like this. In the diagram, the CFG assigns identifiers to restrict indirect branches like number 17 represents the valid path to the RT and GT functions. Number 23 also represents return path to the sort function. And number 55 is the same as others mentioned before. As you see, the weak point of it is clear. That's precision. For example, number 17 can transfer to both RT and GT functions. And number 55 can return to the core site within sort2 function. However, we all know that the more precision we get, the more overhead we have. So it's a trade-off. To overcome this trade-off, there have been so many studies. Some of them reduced the overhead with profiling data and hardware supports, and they also affected real-world CFI implementations. All right, the next is hardware-assisted kernel CFI in use. In the meanwhile, practical CFIs have focused on deployability and practicality. There are several CFI implementations, such as Microsoft Control Flow Guard, Clang CFI, and FineIVT. Especially, FineIVT is the latest one and applied to the Linux kernel. They have similar architectures that combine the software-based CFI with the hardware-based CFI, like Intel Control Flow Enforcement Technology, as known as CET. Reuse attack protector from the PAX team and CNU compiler collection are not mentioned here, but they also support the CFI in their own ways. By the way, what's the InterCT? There have been many talks about InterCT, so I would like to explain it briefly. InterCT has two features, Indirect Branch Tracking, IBT, and Shadow Stack. The IBT feature limits abilities of indirect calls and jumps, so they can only transfer to the end branch instruction. Shadow stack protects the return address with saving it to the protected area. Yep. I know one picture is better than thousands of words, so here are some diagrams. This is an example of IBT. Core RAX and end branch instructions are the core part. So the indirect call can jump to the end branch. However, it can't transfer to other points like the middle of the function. On the right side, it shows how shadow stack works. After function call, the return address is saved to both the stack and shadow stack. After that, the stack pointer, RSP, and the shadow stack pointer, SSP, move down. When the return occurs, the CPU pops return addresses from the stack and shadow stack and check them. It's simple. So what is the hardware-assisted CFI? You already knew that. It means the software-based CFI assisted by the hardware-based CFI. The software-based CFI is effective and has been used widely, but it actually can't restrict indirect branches strictly. They can still jump to any location. In contrast, the hardware-based CFI can restrict them. So the combination of hardware and software-based CFIs can enforce strong CFI policies. Now, it's time to tell you what the hardware-assisted kernel CFI is. It's also a kind of CFI with special features to support various control flows like system calls, interrupts, and exceptions, and languages like C, Rust, and even assembly. Commodity OSs already have their own kernel CFIs like Microsoft CFG for the Windows kernel and Clang-K CFI and FineIBT for the Linux kernel. Especially, the shadow stack of Intel CT is not ready for the Linux kernel yet. All right? This is an example of Clang-K CFI. As you know, Intel CT works like this. And this part is software-based CFI, especially has a caller side verification method. In line number 4, you can see the value FFFA FH6C. It comes from the function signature here, and it's a negative value of the signature. This means that the line number 5 must be 0 if the target of the indirect branch is varied. If not, an exception occurs. This page shows the FineIBT code that is the target of this talk. The difference between Clang-K CFI and FineIBT is the verification point. FineIBT has a callee side verification method like this, and other parts are similar to the KCFI mentioned before. By the way, all CFIs have the same assumption. It's non-writable code. If the assumption is not ensured like line number 5, by changing the sub-instruction to the no operation, the indirect branch in line number 6 can jump to the target function without any checks. In another case, line number 11, by changing the UD2 instruction to the no operation, any indirect branch can jump to the point because the check doesn't work. So this means that all CFIs, including kernel CFIs, can be neutralized without non-writable code, right? Non-writable code for application is ensured by the page tables within the kernel. So kernel vulnerabilities are needed to change the permissions of the page tables because CFI can prevent. Oops, sorry. I would like to say because for other conference, but I have to say if for this conference. So let me repeat again. So if the CFI can prevent control flow deviations like virtual protect and mprotect functions. Yeah. Anyway, then what ensures non-writable code for the kernel? Yeah, just page tables. This picture shows my concerns about it. They have the same privilege, so the page table can't ensure the non-writable code for the kernel, right? So we need the non-writable code mechanism for kernel, not the trust. The well-known and widely deployed mechanism is hypervisor-based based protection mechanism like this. The hypervisor has its own page tables called second-level address translation table, as known as SLAT table, and recent operating systems like Microsoft Windows also ensure non-writable code with it. SX means supervisor execute permission, and UX means user execute permission. In this page, they are activated because of supporting Intel mode-based execution control, as known as MBC. Okay, the picture is a little complicated. Let's see how it works. If the code modification occurs by manipulating the permission of the page table like this, the modification is prevented because the SLAT table is still set to non-writable. If credential modification occurs like this, it's also prevented because of the SLAT table. In this case, code injection occurs by setting the execute bit of the page table. It's prevented too. As you see, unauthorized code modification and injection are prevented successfully. Now, the core part, page-oriented programming. The hypervised non-writable code mechanism and hardware-assisted kernel CFI are effective and worked properly, right? No, it's not true anymore. Actually, the fact is that they were effective and worked because of this talk. Let's check the weakness of the hypervisor-based non-writable code mechanism. As you see, here are two functions. One is system call, and the other is commit CRAs that can escalate your privilege. Commit CRAs is in FF885211, and the system call is in FF881211. Their page offsets are identical. As you have seen, unauthorized code modification and injection are prevented because of the SLAT tables. However, if you remap existing physical pages like this, then you can create new control flow. This means that you can get the escalated privilege by calling the system call with root credentials. This process calls the legitimate function like commit CRAs. So if the credential modification attack is prevented by the hypervisor, this technique still works. Now the weakness of the hardware-assisted kernel CFI. It focuses on indirect branches. Then what cares about direct branches? No, nothing cares about them. Now, I present another and page-level code reuse attacks such as return-oriented programming and jump-oriented programming. Is page-oriented programming, POP. POP exploits the aforementioned weaknesses of state-of-the-art kernel CFIs. It programs page tables with a kernel memory read and write vulnerability to train code pages and direct branches. So POP can make new control flows under CFI enforcement. It identifies page-level gadgets and stitches them to bypass the strong CFI policies. POP consists of 4 stages. The first stage is page carving, which identifies gadgets and system calls from the kernel binary. And the second stage is page stitching. It trains gadgets and system calls to create new control flows. The third stage is page flushing, which flushes the stale mappings in the TLB. And the final stage is exploitation. It just executes the system call with arbitrary arguments. This page shows stages briefly to help you understand POP. Then let's dive into the details. Page carving finds gadgets and system calls. The gadget type doesn't need to be the function. you know. But for simplicity, I chose only the function type for this talk. There are two types of gadgets. One is the core gadget, and the other is the no operation gadget. The core gadget looks like this and has direct branches and connects a system called candidate to the commit CRAs. The no operation gadget unlinks on essential functions within the gadgets or the system core candidates or the commit CRAs. The page stitching stage chains gadgets with data to create new control flows. It remaps a gadget's physical page to the target logical address of the direct branch by programming page tables. It also builds private page tables for exploitation by allocating new page tables whenever remapping is needed. Free pages for them are allocated from the direct mapping area of the kernel in reverse order. Yeah, I know. The page stitching is a complicated part, so let's see with the diagrams. Yeah, the original control flow goes like this, okay? And the new control flow can go like this. If a system core candidate has a direct branch that can reach a core gadget, and if the core gadget also has a direct branch that the page offset is 220, that is the same offset as the commit CRAs, then commit CRAs can be remapped according to the direct branch like this. And remains. So functions also need to be remapped. However, if they are unessential, they can be replaced with no operation gadgets. And this is the final piece, root credentials. So we can escalate our privilege with the argument and the system calls. The page flushing stage is, stage flushes all the mappings in the TLB to apply new ones. There could be many ways to flush kernel TLB. However, I just removed the global bits in shared page table and slept for a sufficient time. As you know, the TLB has limited space, so they can't hold all kernel mappings. So therefore, mapping data which don't have the global bits are flushed first. One thing we should consider is the CPU affinity, because each core has its own TLB. The last stage is exploitation. It's very, very simple. Just execute the system call with an arbitrary arguments on the same core where the page flushing stage was done. 32-bit and 64-bit system cores can be used for the exploitation. Yeah. I can guess what you are worried about. It's so complicated, right? So at this time, this picture shows your worries. You are thinking like, so, do you mean this really works, huh? Yeah, it's okay. It's okay. This isn't the first time. And even my colleagues who work together also did like you. So, and POP is a new concept, so I can understand you and also my colleagues. Seeing is believing, right? The demo is ready for you. Let's see it. Demo time. Okay, I used a laptop from ASUS and also used software listed in this page like LLVM is version 6 and Linux kernel version 6.3.11 with FineIVT. To make the process simple, I executed a kernel driver that has information disclosure and memory read and write vulnerabilities. Additionally, I modified open source hypervisor Shadowfox to support Intel CT and MVC features. And I ran it on the system. The hypervisor was presented at Black Hat Asia 2017. So if you are interested in the hypervisor, please check it. Before showing the demo, I would like to show the reality. It's, until now, you can see the that's the brief version, but yeah. I would like to say Charlie Chaplin, the greatest actor and director, said, "Life is a tragedy when seen in close-up, but a comedy in long shot." But I totally agree, and I would like to say, like, building an exploit is a tragedy when done by my hands, but a comedy by your hands, right? And now it's time to close up. I prepared some complicated diagrams for you to show the tragedy. In this slide, yeah, it's the reality. I prepared and chose two core gadgets, XHCI address device and config.fs open file, and also chose the system core, sysbpf. Then I remapped the first core gadget to the target address of the direct branch. The displacement is -983,000. So the target address is in the core gadget should be changed like this. The second core gadget is remapped, and it's the same as the previous one. The displacement is -27F000 and affects also the direct branch. Finally, CRAs is remapped, and the displacement is 19D000. And the instruction pointer-based values are changed like this. It's just a simple addition, so please check my presentation after this talk. And this is not the end. Let's focus on the CRAs. CRAs updates credentials here and calls 7 functions like this. Okay, these functions need to be remapped. However, all functions are not essential. That means let's replace them with no operation gadgets to evade remapping explosion. The first one is set dumpable. Actually, it has no external cores, so remapping is a good choice. However, I just replaced it with the no operation gadget. And the next ones are these two functions. Unfortunately, they are in the same page. You know, POP use the page level gadget, so in this case, can't use the POP. So there is no choice but to remap them. But as you see, they have function calls like downright and upright, which may lead to the remapping explosion. But fortunately, I could find the if condition and evade it by setting the thread carrying variable to null like this. These functions are also in the same page, but in this case, have only inline functions. That means no external cores, so I just remapped them. The last two functions have external function cores, so for this time, I replace them with the no operation gadgets like this. Yeah. These are diagrams, and yeah, these are the final result. The tragedies end, and this is remapping table of POP. So the POP stitches gadgets according to this table. And it looks like RP table, right? It's very similar. It's really demo time, and I spent so much time drawing the fire on the PC, and the amazing point is that the fire is blinking. Yeah, let's see it. These are tools for the POC, and the first stage is page carving. Now carving tool disassembles the kernel binary. All right, and this is the result. And let's analyze CRAs. Yeah, the page offset is 220 and has several function calls like set dumpable and key FS UID changed. You already have seen. All right. The next stage is page stitching. It trains gadgets and system cores to create new control flows. The demo shows how to find core gadgets and system cores. The result of page carving have information about function addresses and branch targets. So you can stitch them using text tools like grab, like this. Okay, now you can see the system core. Yes, sysbpf. Yeah, stitching is end. And let's find the operation gadgets. Unlinking function is the same process as the chaining process. These are the operation gadgets for it. All right. At this time, the demo shows the POC kernel driver. And to make the POC exploit simple, I located the remapping table of POP in the kernel driver. If you want, you can move it to the POC application with your vulnerabilities. Now the driver is executed and exposes sensitive symbol addresses and the vulnerable interface. And now, the hypervisor, shadow box, runs like this. Yeah. So unauthorized code modification and injection are prevented from now. Now, page flushing and exploitation stages. The POC application calls sysbpf with malicious credentials like this. RAX has the system call number, and RDI has the address of credentials, and the syscall instruction is called like this. And as I mentioned before, the application is executed on CPU 0, where the page flushing will be done. All right, let's start POP, and the fire is blinking now. Yeah, it's hard. Before POP, the application has user privilege, so it can't read the etc shadow file like this. Now POP is running, and these are logs from the POC driver. The global bits are cleared. And now POP is done. Now the application has root privilege, and it can read the etc shadow file like this. Thank you. Thank you. And yeah, you like trust me a little, right? Okay. This is a bonus page. As you see, there is the end branch instruction of the start point of CRAs. So, if you find an indirect jump, you can chain gadgets like this and call CRAs. This is simpler and more intuitive than the previous one because the remapping of CRAs is not needed. Yeah, it's very similar like the return-oriented programming. Conclusion. All right, mitigation of POP is not simple, because the page table is the essential part of OSs and changed very frequently. Many researchers have introduced their own ways of escorting page table updates with hypervisors, but overhead still remains. The latest inter-CPUs support the hypervisor managed linear address translation table, as known as HLAT, to prevent page remapping attack like POP. But HLAT tables translate logical addresses of the kernel to physical addresses instead of page tables in commodity OSs. That means hypercores are needed to update HLAT tables within the hypervisor, so it's very frequently. So it could be another opportunity for you and me. And the more critical point is legacy systems are still vulnerable. So it's an open problem now. Now, conclusion and bracket soundbites. I would like to say, state-of-the-art kernel CFIs are effective, but has weaknesses mentioned before. So, I have proposed page-oriented programming, POP, a new coder user attack that can subvert the kernel CFIs. It exploits the weaknesses and can create new control flows under strong CFI enforcement. Mitigation of POP is an open problem now. Although Intel developed HLAT, it needs interactions between the OS and the hypervisor. So the changes can give us new opportunities. All right, this is the last slide of my presentation. The picture shows what I want to do and what I have to do after this talk at the same time. And here is my project link. So if you are interested in the project, please check the link. My code will be released soon after this talk. All right, I hope you enjoyed my talk, and thank you for listening and your precious time. Thank you.